to read this slide. Yes, go ahead.
Transformation of the plane or one-to-one correspondence between the point and the plane that demonstrates a change in position or fixed position between the point and the plane.
Good. Transformations, because there's a one-to-one correspondence, means that every transformation in the plane is a one-to-one function. And because it's a function, what we can do is we can actually state the domain and the range. So added to your notes, please make sure that you add the domain and range to it. So let's talk about the domain. The domain, being that we're talking about this is the coordinate plane, and we're not talking about any specific point, we can state that the domain is all x such that it's all points in the plane. And we can say the range is for all y, which is all points in the plane. So please make sure you add that domain and range to your notes. It's important that you know it's their one-to-one function. It's something that could come up, that you know that it is a one-to-one function. We have to prepare for that reading again. So this is part of our review for that. Note with any transformation that you do, and you guys know what the transformations are. It could be a reflection, a translation, a rotation. One of those three, even a dilation, it's going to be one-to-one. 1 point can't go to 2 points. All right, we talked about the domain of the function. All right, so in this slide, we're going to talk about what a line reflection is and a point reflection. And after I get some volunteers to read this, we'll go over what the symbology means to remind you of that. And we'll point out some of the pictures on the slide. I have volunteer to read this slide. Somebody else. Yes, Drew.
Line reflection. One triangle will coincide with the other. We fold this page along line y equals negative x. The line of reflection. Point A corresponds to A prime, B to B prime, and C to C prime.
All right, so I want to make sure that you guys are aware, when you see this A with a little apostrophe, that we call that A prime. So, very good, Drew. This is B to B prime and C to C prime. And here's a picture of here. If you look at my symbology, whenever it's a line reflection, you see a little r. So little r, make sure you take a note, always means a line reflection. In this case, it tells you the line is y equals negative x. And if we were to actually be able to take this and fold it in half, we would find that it would be all the points would correspond with one another. You just have to picture it three-dimensionally, if you could actually fold it. Point reflection. Julia?
Point reflection. A reflection in a point P is a transformation of the plane such that 1, the image of fixed point P is P. 2, for all other points, the image of K is K prime, where P is the midpoint of K prime.
Okay, so let's look at this. And let's talk about the symbology. When you see a capital R with a point, say in this case point P, and point P in this problem is going to be what? What do we call that point I just circled? The origin. Point P is the origin here. Okay? And if point P was something that was labeled on this graph and I did a reflection through point P, where does point P go? Same spot. That's what 1 says. Now, they're saying that for all points K, and we have here points MAC. And for my symbology, I said we have a reflection of point P through A. So if we were to look at this, we could see that with each point, say for A, I have to go down 4 and over 4, and I have to go down 4 and over 4 again. And that's showing that I'm doing a reflection through that point. The same way with M, which I'll do in another color. Here I have to go down 4 and over 2. So to reflect through that point, I have to go down 4 and over 2 to get to M prime. Okay? So please be aware of what you need to do to get to the points, and that you know that this means a reflection through a point. And here you can see the reflection of point P of A gives you A prime, and this for all points on that figure that we have on this coordinate plane. Question? Rotation. Do I have a volunteer to read rotation? John?
The transformation of the plane about a point of called the center of rotation is through an angle of theta degrees such that the point lines up to for all the points that is x is x prime, you measure an angle x o x prime equals theta x o x equals o x prime.
Okay, so here we're dealing with this picture right here. My center of my circle is point O. And if I did a rotation about point O, where does point O go? Same spot, it doesn't move. But then in my symbology, this says rotate about point O. So it's just like a point rotation, but this is telling you, whenever you see that comma, this is telling you how far to go. And in this case, 30 degrees. So they want you to move point X 30 degrees. And according to my notes right here, clockwise rotation is negative, counterclockwise rotation is positive. So because there's no negative sign here, we're assuming it's a positive rotation at 30 degrees. And I'm not sure if this is exact, but this is approximately a 30-degree rotation. All right? So we're going to assume that to be true. It may not be to scale, but it's a good approximation. And you can do it with more than just a point. Here's a figure. It could be anything. You know, in this case, it's you know, there has to be some sort of points that made that figure. Every point in this figure got rotated, all right, in some positive angle. Questions on rotation? Next slide, translations. Rebecca, can you read this one, please?
Translation is a transformation of the plane that shifts every point in the plane the same distance in the same direction for a second.
All right, and the symbology for this means a translation, move XA, move YB on point XY. So for every point, that's going to be, you're going to add that value of A to X, and you're going to add that value of B to Y. Now here, if I was to look at this, there must be, you know, while my A value is probably positive here, my B value is probably what? Negative, because it's going, this is going down one. Every point went down one. All right, so this is obviously a move in the A direction. Here A would equal 1, 2, 3, 4, and B would equal -1. So this, on this figure, this is a translation of 4, -1. Questions on translation? Dilation. Dilation. Volunteer to read this, Matt?
Dilation of K, where K is a positive number called the constant of dilation. Transformation of a plane such that the image of O, the center of the dilation is O. For all other points, the image of A is A prime. For the ray OA and ray OA prime, the same OA prime equals OA
Times K.
times K.
Right, I couldn't find a regular multiply symbol, so that's the best I could do. I apologize for that. The symbology here is just saying, one way that you can see this is with point P, change it to be some multiple K to X and K to Y. Not all the time when you see this, when you see from here to here, is the value of K going to be the same? But most cases it is. But when you see this, a dilation of K, it automatically means that you multiply both X and Y by that K value to get the point KX, KY. Now, it is in general terms, if it was a coordinate plane, what would our center most likely be, or what would our point O be? The origin. It's always from the origin. And when you multiply the origin by some value k, where does it go? It stays there, all right? So we know that the center, that the point of dilation never goes anywhere. And they're saying that there's some multiplier that you're multiplying this point A by, that's gonna give you A prime, all right? So there's some dilation k that's moving this A to A prime, this C to C prime, and B to B prime, all right? That's all that's saying. Any questions? Line reflections. These are the rules that you guys, if you want to, can memorize. And I'll show you that the fact that I don't memorize them, all right? If you want to take the time to memorize what a reflection in the x-axis is, here's the symbology, is any point xy goes to x negative y. Any reflection, this should be y-axis. Any reflection in the y-axis turns point xy into negative xy. A reflection of the line y equals x changes the point to yx. Sounds like an inverse function, doesn't it? Inverse functions, we learned, is a reflection of the line y equals x. A reflection in the line y equals negative x, it changes any point xy to negative y negative x. All right, if you want to, you can memorize that. A point reflection about the origin. You can think of it either a half turn or a rotation of 180 degrees. It means the same thing. And any point xy goes to negative x, negative y. Now I'm going to show you what I do. I'm going to treat the smartboard as my piece of paper, okay? And I'm going to see what a reflection the x-axis is going to look like with my point xy. And this is what I wouldn't mind you guys doing as well. You know, I actually think about it in my mind, or I graph it. So here I can take this and I can flip it up down. Where did my point go? How would we name this point? It would be a positive value of x and a negative value of y, which is a reflection, which is what it says a reflection of the x-axis is. So I'm going to flip it back. There's my point. A reflection of the y-axis. I actually go ahead and I flip it, so I don't have to memorize that rule. So I'm going to flip it left-right. I now have a negative value of x and a positive value of y. A reflection of the line y equals x. I can't do that here, unfortunately, but you can think about it and actually draw the line if you want. The line y equals x, everyone knows what that is. We can plot some points. And you guys should already know that a reflection through the line y equals x is just like the inverse of a function, and another definition of inverse of a function is you switch x and y. But if we were to reflect that, it would end right here, and that becomes yx. If we wanted to do a reflection in the line y equals negative x, you could go ahead and draw that line if you wanted to. There's a close approximation of it. My point disappeared. And that would reflect, you would do a visual reflection of that. I don't like memorizing these rules. It doesn't take very long to draw yourself a picture. You're going to have graph paper, that graph paper page on your Regents exam. Use that if you have some sort of question like this. If you're somebody that likes memorizing this stuff, go ahead. Rotations about the origin. If it's a counterclockwise rotation of 90 degrees, here's what you're going to see is the symbology. Any point xy goes to negative yx. A rotation counterclockwise of 180 degrees is going to give you negative x, negative y. A counterclockwise rotation of 270 degrees about O, center row, which is the origin, any point xy becomes the point y negative x. Again, if I didn't want to memorize this stuff, what am I going to do? I'm going to rotate it. Where did my point go? This is, my original value was 3, 2. I'm now at -3, or this was 2, 3. My new point is -3, 2. So it did become negative xy. It proved it. I would also, if I want to go further, do the 180. You can see my point became negative x, negative y. Just like it would with a point reflection. If I did a point reflection about the origin, I would lay in the same spot according to the last slide. 270, I had to go another 30 degrees. And here, you can see that instead of it being 2, 3, it's -3, 2. All I did was actually rotate it. And probably on the Regents exam, most likely what you're going to see is a rotation of 90, 180, or 270, or some multiple of 90. What if it was in the clockwise rotation? I didn't put that information up there, but what's mathematically equivalent to a clockwise rotation of 90 degrees, or a rotation of -90? The same as a counterclockwise rotation of 270, right? So if you're somebody who likes to memorize this stuff, add that to your notes to know what the rotation is. Otherwise, is there anything wrong with picking up your piece of paper and rotating it 90 degrees and reading the point? No, there's absolutely nothing wrong with that. That's what I suggest you do. Dilation. Or a translation. A translation of A units horizontally and B units vertically. What is the name of my point right here? 2, 3. If I'm going to do a translation of -5, 2, what's going to be my new point? Raise your hand. Let you figure it out. John? -3, 5. -3 up to 5. And I can call this my A prime, if this was point A. Okay? And I would label that also with the point. -3, 5. So if you're asked to do that, I would make sure not only plot the point, but label it. So if you made a mistake with the plotting, you would get credit from naming the point. Dilation. If there's some dilation k on xy, multiply both x and y by that dilation number. I have a dilation number of 3. Here's my point, 2, 3 again. Megan, what's my dilation of 3 going to be on that point?
Oh, 6, 9.
6, 9. So I'm going to go over 6, 1, 2, 3, 4, 5, 6, up 9. Label it. And if this was A, I'd label this A prime. Questions on translations or dilations? Hopefully you added this to your notes. I have these pictures here for you. All right, now we're going to get into some of the other stuff, just some additional vocabulary. Please make sure you're aware of the term symmetry and that there's 3 types of symmetry. There's line symmetry, there's point symmetry, and there's rotational symmetry. Hopefully, I have the definition up there. We've talked about symmetry before. We talked about the line of symmetry in a parabola. Looking at these, 1, 2, or 3, which one of these is a line, has line symmetry? The middle one. So here's the line symmetry. Which one has point symmetry? The third one, this is point symmetry. And what is, so then that makes this one the rotational. This does not have point symmetry because where would this point, traveling to that point of the center, would have to travel that same distance, and there isn't a point there. So that does not have point symmetry. It's important to know that under line reflection, point reflection, rotation, translation, the following properties are preserved: distance, angle measure, parallelism, collinearity, midpoint, betweenness, and area. Only under dilation do distance and area are not preserved, but everything else is. All right, it's important that you know those definitions as well. Again, you never know what type of question may come up on that Regents exam. Question on any of the symmetries or properties? Yes. If 3 points are in a row, you'll have 3 points in a row again. All right, this was one of the problems that came up, which is why we need to go do this lesson. Here we have, we're talking about isometries, and there's two types of isometries. There's a direct isometry and an opposite isometry. A transformation that preserves distance is called an isometry, but a direct isometry preserves distance and orientation. An opposite isometry preserves distance, but changes the orientation. So which of these two, I'm telling you two of them, are a direct isometry, 1, 2, or 3, and one of them's an opposite isometry. One is direct because we can see that we're going counterclockwise here, and we're going counterclockwise here. What about the middle one? I hear direct, I hear opposite. This is opposite because here's EFG. It's clockwise. EFG here is counterclockwise. Notice the change in the arrow direction. That's what makes it an opposite. And how about this one? Direct or opposite? This is counterclockwise. What direction is this? So what is it? This is a direct isometry. You actually have to take that time and actually make those arrows to make sure the arrows are going the same direction. Now, did A and B move? Yes. But the orientation did not change. This was a point reflection about point P. Point reflection maintains a direct isometry.
So it had nothing to do with the shape, just.
Has nothing to do with the shape changing. It has to do with when you look at A, B, and C, or whatever letters are in order, that the arrow direction for counterclockwise or clockwise is exactly the same. Composition and transformation. You guys know what composition is. If you see that open circle right there, in layman's terms, we've done this before, we've done compositions. I'm not going to spend a lot of time on this slide. Do this one first, followed by this one. You do this second. All right? Everyone knows composition of functions. If this was a closed circle, what would we do? We do this, then this. All right? Please make sure you're aware of that. One of the things you're going to see on your worksheet today is that sometimes you're going to be asked to rename your composition. Here's a composition of functions where first you reflected this shape. So this was our A. The triangle is A. A reflection to our y-axis gave us triangle A prime. And a reflection in the x-axis gave us A double prime. But this is saying that these two reflections could have been done in one step by just doing a reflection in the origin. All right? By doing a reflection in the origin, you could get there in one step. So you're going to see the same thing. I think it's the last couple problems on your worksheet that you're going to do. is that you're gonna actually do a reflection. Glide reflection. What glide reflection is that in one of two ways, either reflection on a line or a translation, or the translation first and then the line reflection. That's called a glide reflection. There's a three-line reflection theorem that every isometry that exists is equivalent to the composition of no more than 3 line reflections. So if you know you have an isometry, you can find that isometry, if you don't know what it is, in no more than 3 line reflections, if you actually take the time to do that. Questions? During the remainder of the period, what we're going to do is we're going to get into small groups, and you're going to work on a worksheet I'm going to pass out to you right now. So once you get this, please get into groups of 3. And you're going to talk about all of the evens, 2 through 42 even. It should go pretty quick. You're using all of the information that's from the slides. You have the slides with you. Go ahead and get into your groups. I'll come around and scrap and me for a moment. Quick to get together. One too many. This group. Yeah. I'm going to give you direction on that. Skip 2 through 8 for a moment. Just start off with number 10. All right.
Yeah.
We're going to work right to the bell on this. For homework, I want you to do the evens on that worksheet. Yes.
I already got it.
On 2 through 8, guys, what I want you to do is first, tell me if there's a line reflection. B, tell me if there's a point reflection. And C, tell me if there's a rotation reflection. Point reflection. Wouldn't there be a point? You put a point right there? Yes, we need. We would end up with another point. How about point reflection?
Reflection in the origin. Reflection in the origin.
There is a point. There is, because you can state where that point is, right here. Because if you were here, you had to travel to that point. You have to travel the same distance away. You were laying right here. You can do that with all the points. What type of?
Yeah, you switch and, oh wait, no. you
What are you saying about, is there a line reflection? Point genius. How about rotation? Do you rotate this? Will you get the same picture eventually without going all the way around?
Wait, How can you dilate the horse? How can
Yeah,
you
at 180 degrees.
That's what I'm saying.